All right, so this is lesson 8.3. In this lesson, we are putting together our exponential growth and exponential decay functions. So we've looked at them individually in our two previous lessons. Putting them together means that we want to be able to determine or identify before we start anything else whether or not the function we're working with is growth or decay. And the reason is because if we're going to create a graph, then we need to know whether or not to include a y-axis reflection or not. So this prior knowledge problem says to rewrite the function with a base of 2. So this has to do also with understanding the different ways that we can represent decay. So this is a decay function here with a base of 1/2. If I want to change it to having a base of 2, then what I'm going to have to do is take this power of 2, which is in my denominator, and move it up. And that's an application of what we call the negative exponent rule. And we usually use the negative exponent rule to change a negative exponent to a positive, but the reverse is possible also, like here. So if I pull that 2 to the top, then that exponent of +1 becomes a -1. And then the exponent property says I would multiply those together. So this gives me 2 to the negative x. So this goes along with what I was sharing in the previous lesson, that there are two ways to write exponential decay functions, and they're equally common. All right, there's no preference one over the other. So we have to be comfortable with both. One is by using this structure. That's our base, which is equivalent to our base of 1/2, which is the second way. So remember that a decay function has a base that is positive but less than 1, and we call that being between 0 and 1. And so both of these, whether it's directly a 1/2 to the first power or a 2 to the negative first power, both of them represent the same number, which is a number less than 1, making them a decay function. All right, so this gives us just a reminder of an exponential function structure shown here, showing our parameters of a and h and k, and then also c. So one of the key things to remember is that b to the power of c, that's our base. So you can't just look, say, at the normal b value, base value in the parentheses, and be certain if you have growth or decay. You have to take the coefficient of x into consideration. And I say coefficient of x because if I distribute c, I get cx. So c is the coefficient of x if it's not in factored form. Another thing that I want to point out to you is that you're going to want, for graphing purposes, this factored form. That's the only way you'll correctly get the h value, which is going to determine your horizontal translation. So going back to your base, which is b to the power of c, remember that if it's a growth function, then that base value, b to the power of c, is going to be greater than 1. But if we have a decay function, then that b to the power of c is our base value and will be between 0 and 1. So it's still positive, but it must be less than 1. All right, so in these examples, we are going to look at identifying whether we have growth or decay, and then also including the base in that, which will basically be our justification also for whether we have growth or decay. So let's take a look at this first function over here. F of x equals 4 to this 1/2 to the power of negative x plus 4 minus 2. All right. So we're going to start by figuring out what the base is, because that's really going to tell us whether we have growth or decay. So like I said, you can't just take the number inside the parentheses and use that as your base. You've got to consider the coefficient of x, which here is a -1. Another thing that I want to point out, which is where we'll be going with this, is that if we were going to graph this, which we will be in our problems, we'd want to factor out that -1 from the negative x plus 4, and that would give us x minus 4 in the parentheses. That's the only way we're going to get the correct H value for graphing purposes. But if you just want to identify it as growth or decay, you can use the factored or the unfactored form. So this 1/2 to the power of -1, that is our base. And remember, anything to a negative power means a reciprocal power. The reciprocal of 1/2 is 2. So this is the same thing as 2 to the first power, which is 2. 2 is greater than 1. So this is exponential growth. That's important because if we were going to graph this function, we would know not to include a y-axis reflection. We only want to use a y-axis reflection if it's decay. So we would start with our points that are our powers of 2, which is our growth situation, and not do a y-axis reflection to make sure it stays growth. And we also want to indicate our base, which is 2 in this case. All right, let's take a look at the second one. So here we're looking at g of x, and we're looking again to identify the base. So remember that, and it's right here, your base is your b value, which is what we normally think of as a base, but to the power of c, which is the coefficient of x. So here in this problem, my coefficient of x is 1. So my base is this 1/2 to the first power. Anything to the first power is itself. So this is 1/2. 1/2 is positive. Remember, the base of every exponential function must be positive. There are no negative bases for exponential functions of any kind. So being positive isn't enough because they're all positive. We have to compare to 1, and it's less than 1. And that tells us this is decay. So this is exponential decay. And that base value would be 1/2, like so. So in our third one, h of x, again, our base is b to the power of c, where c is the coefficient of x. The coefficient of x here is -1. So we're looking at our base here being 10 to the power of -1. Again, anything to the negative exponent is a reciprocal power. So this would be 1/10 to the positive first power, which of course would be 1/10. 1/10 positive, which it should be, and is less than 1. So this is also exponential decay. And the base in this case is 1/10. Now, what's important about identifying the base as being either a power of 2, like the first two. So the first two, we have a base of 2 and a base of 1/2. Both of those are powers of 2. The third one is 1/10, which is a power of 10. They tell us if we're going to graph which of our key points we should use. Should we use the points that are the powers of 10, or should we use the points that are the powers of 2? So that was from our previous lessons also. If we have a base of 2 or 1/2, then we use our points that are the powers of 2. So -2, 1/4, -1, 1/2, 0, 1, 1, 2, 2, 4, 3, 8, where the y values are the powers of 2 and the x's are the exponents. Whereas over here, if we're going to have a base of 1/10 or 10, then we use the points that are the powers of 10. So we have -1, 1/10, 0, 1, 1/10. And those were the three that were doable with graphing by hand, where the y's again are the powers of 10 and the x's are the exponent value. So 10 to the negative first is 1/10. 10 to the 0 is 1. 10 to the first is 10. That idea. All right, so for this lesson, because we've already talked about graphing, both growth and decay, These are the only examples because the only new information that we need to understand is how do we recognize or identify whether the function is growth or decay. Then we know whether to include a y-axis reflection, which we would for these two because they're both decay. And we have to, of course, know what our key points are that we would be transforming for that graph. So that finishes up this lesson.